Upload the sketch and connect the microphone. This is going to be one of my no bullshit guides videos, where I will tell you about audio input, audio output, and machine learning inference on audio signal with Raspberry Pi newest chip RP2350. Although what I will show you by large extent can be applied to RP2040, it's faster on RP2350. Let's start with the stuff that we need. I have Raspberry Pi Pico 2, the extension shield with groove sockets, which originally was made for the first Pico board, but works just the same with the second. Analog groove microphone, two I2S microphones, amplifier, and a pair of 5-watt 8-ohm speakers. Plus a bunch of DPON and groove cables. Links for all of this are in the video description. Our first task is audio input. The simplest test you can imagine, and you should always start with the simplest test, I'll tell you later why, is to get the samples from the microphone and output them through the serial port to either just see them as numbers or plot them as a sound wave graph. Plug the analog microphone into A0 port, install the 4.2.1 version of Raspberry Pi Pico Arduino core. It is preferable over official Arduino core for Pi Pico, partially because it's more developed and less buggy, but also because the official core does not yet support Pi Pico 2. Open up an example ADC sketch and upload it. We should see the sound wave on the serial plotter, which changes as we speak something near the microphone. Hello, Hawk, this is Stork speaking. Increasing the gain a bit by multiplying the resulting values can be helpful. Let's do that. One, two, three. Okay, this is a test, and this really seems to be working. Analog microphones are the simplest in terms of getting the samples from them. Just read the analog values like you would do with any other analog sensor. The obvious disadvantage is that we get quite a bit of noise, which gets progressively worse if we use longer cables or if there are sources of static near the device. The solution is to use digital signal transmission protocol. In that case, I2S or inter-integrated circuit sound. That's a mouthful. Connect the microphone to the board. The wiring can be a bit tricky because different naming is used in different guides for different microphones. In this case, D out corresponds to SD or serial data, B clock corresponds to SC or serial clock, and left-right clock is word select or WS. Upload the I2S input sketch and use the wiring from the sketch description. So serial data is connected to GPIO 0 and so on and so forth. Okay, so you will see the sound wave on a serial plotter. You can see that the range is getting much larger if I speak near the microphone, which is a good sign always. Now, why do you want to start with this dull example and not something fun and useful like recording and playing the audio or recording into WAV file? Well, when starting out with the new hardware, it's important to have as few points of failure as possible. If your code is that simple and you know it works, if something goes wrong, you know it's either wiring or the hardware. If you screw up the code but don't know about it, you might be tempted to look for a hardware issue when it's not really there, and vice versa. So, start simple. Now, when we know the mic works, let's add the playback code. And again, start that simple. Wire up the amplifier to the board and speakers to the amplifier. Upload the playback code and do some. Once Macarena is done, let's modify the code to record a 2-second sample from the microphone and play it back through the speakers. Okay, this is a test. Everything seems to be working fine.
Everything seems to be working fine.
And for the last piece, let's use the audio input to do something actually useful with it and recognize the keywords with machine learning model running on RP2350. I made a video about using synthetic data to easily train a keyword spotting model in under 10 minutes with Edge Impulse. You can follow the guide to train your own model or simply take the public project that I shared, which I used for robot spider control. Download Arduino library deployment and place it into your libraries folder. It has different location on different OSs. Open RP2040 microphone continuous example. It will not work right away because we're using a different microphone. But it is not a big issue since we know how to make microphone work by now. I'm using the analog microphone here. So I changed the microphone setup function to start analog sampling on pin 0. We have that here. And execute the callback, data ready inference callback, when ADC buffer is full. The sampling frequency here is 16 kHz, which corresponds to the sampling frequency the model was trained on. Inside of the callback, we just check how many bytes of data are available, and then we write them from the ADC buffer to the inference buffer and applying some gain while we at it. With this callback, we can use some of the behind the scenes magic to sample the microphone without relying on any of the two Cortex-M33 cores. So they can do the heavy lifting of neural network inference, which is exactly what is done every time run classifier continuous is called. The neural network inference magic does not need to be modified specifically for RP2350 and works with all the available hardware acceleration as is. Forward, left, right. And also, by the way, here are the numbers for the same code, but with RP2040. As you can see, the difference between the old chip and the new chip is quite drastic. It's mostly due to the presence of floating point unit and also the vector extensions for accelerating neural network inference. Now you know how. What about what? While I'm working on more cool robotics project, check out the RP2040 powered quadruped robot with voice control, or the whole playlist about running tiny AIs on microcontrollers.